Hello everyone, today I'll show you how you can do this blueprint that lets you place these navigation arrows on your paths to guide your players, and also it can indicate with the color coding the speed that they should take. It's a really popular feature in all of the racing games. You can see that the arrows are automatically pointing the direction of the spline. You have the ability to choose the offset between the arrows and also the vertical offset from the spline that you have drawn. Another feature is that these arrows are hiding when you're far away from them. You can see that they're fading away. It's easier to see when there are more of them. So here I'll hide the spline, and now you'll see that the arrows are visible only when you're close to them. And this is also quite usual for racing games. I have the tool already created here, and it will be a little bit easier just first to have an overview how it's working, and then I'll show you how you can build it from the ground up. This is the blueprint. Everything is done in the construction script. The sequence note is doing every step in order, so starting with this 0 index, the first thing that the blueprint does is calculating the size of the arrow, which is taken from the model plus the offset that you inputting in the blueprint, this one here. So calculating the size, and based on that size, calculating how much of the arrows are fitting into the length of the spline, and for each of them you're calculating the position that you need to place them, and then the rotation that the arrow needs to have in order to point in the right direction. The next step here, the index 1, is setting up an array that you use to color code the arrows. Here you can see that the arrows start from green, and here on the first dot they're becoming red. That's because in my array I have values set that change the color, so by default all of the arrows will be green, and for any of the dot you can set this parameter to determine the color. Now all will be red. If I put here 0, you'll see that from red they're becoming yellow, then green, yellow again, and red by the end of the spline. So this is the second step, preparing this array here. And the third one, this one, it reads the values from this array and applies them to all of your arrows in order to make the color appear as you set it up by the parameters. This is all that needs to be done. This overview, I believe, is helping a bit, because if you start just node by node, it's a little bit hard to follow what we'll do by the end. But now that you have seen it, it should be easier for you to follow up the tutorial. Okay, let's start with a new blueprint. Create a blueprint class. It should be an actor in order to be placed in the scene. Let's call it arrow spline tool tutorial. And inside you'll need two components. One will be the spline, and the other will be HISM node that you will place the static meshes inside, and they will be drawn as instances in order to use just one draw call. It's a little bit better for performance. Let's start with the construction script. As I said, first you'll calculate the length of the arrow, and you'll need a way to set up the mesh. Let's create a variable called mesh, and it will hold a static mesh type object. It will be public, so you can set it up here into the world. One other variable will be the arrow offset. I'll rename that to arrow mesh. Arrow offset will be type of float, it will be public again, and then arrow length, it will be a float again, but it will not be public. This will be calculated by those two, and it will not be able to be changed by the user into the settings of your blueprint. I control drag the mesh into the blueprint editor. Otherwise, if you just drag it, you should choose the get arrow mesh. Taking from the arrow mesh the bounding box. This is the box encapsulating the mesh, and if we split this pin, we'll calculate the vector that is containing this mesh. So we'll subtract from the maximum, we'll subtract the minimum, then we'll break this vector and only take the x value, because we only care about the value for the direction that our spline is going, and this is the x. And we'll set this as an arrow length. Out drag this to choose the set, or drag it and choose the set command. And now we'll set it to the x value of this vector. We'll add the offset in order to be able to input this offset, so your arrows are not standing always next to each other. And that is setting up our length variable, and we'll now use it to place all the arrows along the mesh. First, let's set the static mesh for our instances. We'll choose the mesh that we have as a public variable, and then we'll use a for loop to place all of our instances inside. We'll add an instance to our HISM node, and now we need to calculate the transform for each of them and how much we need to place them by these indexes. So first, let's calculate how much times we need to place the arrows into our spline. So getting the spline length and then dividing the length by the arrow length that we calculated. This will give us the number of arrows that can fit into our spline length. We need an integer number because we need to put the full arrow, not 5.2 arrows. So we will just floor to the nearest integer using the floor function. If this division returns 5.2, this floor function will just give you the 5, and we can use this for the index. So now we'll execute this for loop for each index from 0 to the result of this division. And for each of the instances, we need to calculate this transform. Let's split it. We'll calculate the location and the rotation for these arrows, and we'll use a constant scale of 1. You can even put a variable to control the size of your arrows. First, let's start with the location of the arrows. For each iteration of this loop, you get the location at spline, at distance along spline, and this distance will be the index multiplied by the length of the arrow. This will return the position for your arrow that needs to be placed at the current index, and we'll input it into the location transform. We'll just need to add the offset for the z axis. As you can see, I have this variable arrow vertical offset that controls how far the arrows are placed from the spline. That's helpful if you have a mesh for your road that's higher and you need to offset the arrows over this mesh. So let's add another variable called arrow vertical offset. This will be again a public variable, and we'll use it. We'll break this vector. We'll split this transform pin. The x and the y will be directly from our calculated position, and the z will just add this variable, and this will let us control the value for the z location. Now that we don't have still the rotation calculated, you see that our arrows are being placed. We can control the offset, we can control the vertical offset, but if we have a turn in our spline, they're always facing the direction that we started the spline. We need to fix that by calculating the proper rotation, and this is done by taking the position of the next arrow and orienting the current arrow to point for the next one. This one here needs to point to this point on the curve here, where we will place the next one. It's easily done by the same logic that we have here. We just take the position not for the current one, but for the next one. We take the index plus 1 instead of the index, and we have the same get location along spline distance, just the distance is for the next one and not for the current one. Then we'll subtract the vector for the next one and the current one, and this will give us the resulting vector between the two positions, and we'll make rotator from the x-axis and set our rotation here. Now if I compile, you'll see that the arrows are now pointing in the proper direction. You can have a variable to control the scale. I'm currently not doing that, but you can add it later. So this is the first step for placing our arrows. The next step, as I showed you before, will be to make an array where we can put our values to color code the arrows, as you can see here. We can make them green and red. Now for our new tool that we are doing now, it's still not possible. Let's start with adding the second step. We'll put a sequence node here that's first going to execute our placement that we already did, and the second step will be, as I showed you in our already done tool, it will prepare this array. It's a little bit confusing watching it here. I'll try to explain what it's doing, because at the creation of the curve, you don't want to remake this array, you want to save the array that you already had and just add a new value when you add a point, or remove one value when you delete a point from the spline. So you can see that we are getting the number of the spline points and comparing to the length of the array that we already have. And if the array is, if the number of points is bigger than our current array, we are adding to the array, and if it's smaller, we are removing from the array. This is the basic logic. It's a little bit confusing with this crossing lines, but I opted out of making variables for each. Okay, let's start recreating that. We'll have a branch node, and for our condition, we'll get number of spline points, and we'll compare to our array. We'll make now an coloring array. It will be of type float, and our variable type will be array. Let's get the length of our array and compare it to the number of spline points. If the number of points is bigger than the length of our array, like for example now we have 3 points, but the array is basically empty. So now what we need to do is have a for loop, and our for loop needs to be executed from the current length of the array to the number of the spline points that we have, and each time we'll add an element to our array. This should be the same like we had here. Actually, we need to subtract one for the loop. Like this. Because our length and our indexes are offset by 1, because your index starts at 0. So when you have 3 elements, the indexes will be 0, 1 and 2. That's why we need to subtract 1 here. And if the length is actually bigger, this condition will be false. We'll have the opposite. We'll have the for loop, and we'll remove index from our array. The index will be this one, and it will be the opposite. The first index will be the number of the points, and the last index will be the length of our array. As you can see here, this should now work. Let's make this array public so we can check. I have this spline selected. Let's compile and save this. And this should not now be working. We should have our array with the proper number of points. We can see that we have an array with 3 elements. If we add another point, Now we have 4 elements. If we remove 1 point, we have 3 elements. This should be fine. We now need to make use of these values to properly cover our arrows. This requires some work in the material. Again, I'll show you first the already created material and I'll recreate it after, because it's easier to explain when all of the nodes are already here. We use an emissive color and opacity in our material. Let's just care now for the color, because the opacity is just the hiding when we are at bigger distance, as I showed you earlier. So just care now about the coloring. The coloring is using an per instance custom data from our HISM node, taking the custom data from our element and using it to drive the red and the green channels for our color. When the value we have is 1, for example, the red color being 1 and the green one being 1 minus 1, so 0, and the opposite will be when we will have 0, the red color will be 0, but the green will be 1 minus 0, so 1, and when we will have 0.5, we'll have 0.5 for red and 0.5 for green, and so on. So that's how we make the color transition from red to white for each of the arrows between our points. And we set the material color here. Let's care later about the opacity. Let me recreate now this in a new material. I'll call it distance tutorial. We need the material to be, actually for now we don't need the transparency. We can use the unlit option here, and we'll make the logic that I showed you. Use the per instance custom data. We need a vertex interpolator for the red channel, and we need one minus and vertex interpolator for our green channel. And now if we use this material for our arrow, we use this new material for our arrow, we can test if it's working by setting up into our tool this custom parameter. Let's do it just for testing. Let's add a third step here. Add a for loop, and now we have 0, 1 and 2 indexes. Let's do the for loop start from 0 to 2, and for each step let's set a custom data value for the index of the instance. Actually this is for each arrow, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10. Let's do it from 0 to 9 then. And for each index let's set the custom data index of 0 and the value to 1. And what we'll need to do in order for this to work, we need to select in our components view the instance static mesh component and set the number of custom data floats to 1. So we'll have a 1 float. It will be with the index of 0. So here the custom data index is 0 for each of them, and the value we set is 1. And now you can see that each of them is taking a value of 1 and it's becoming red. If we put the value of 0, it will be green. If we put it 0.5, it will be yellow. And if it's closer to 1, like 0.8, it will be orange. Now the question is, first of all, how to calculate how much arrows we have currently, and then what should be the value for each of them. How to calculate how much arrows we have, we already done that into the first step. Here for this for loop, we are placing each arrow with this logic. So we will use the same one here. This will now be executed for all of the arrows. Let's set the value for 1, and you'll see that all of them are red. Let's set it to 0. All of them are green. This part is done, and now the trickier part, to calculate the value for each arrow. We don't want to input the value for each arrow separately. We want to use the control points of the curve that can be a lot fewer than the actual number of arrows that we draw to set up the coloring. And this is why we have to have some kind of calculation that interpolates the color between the 2 points. Let's do the same as we did before. Let's first look at the already done tool. You can see that we're taking the position of the arrow the same way that we did it here when creating the instance. We're just using the world space instead of the local one, and then we're using this function to enter the value for coloring into the array. Now let's do the same here. Let's copy the logic for the placement. Use this index here. And now we need to create the function that will return this value. Let's look at the function and what it's doing. Based on the location, the world location as an input, find input key closest to the world location. We return a value based on the distance from the closest point to the spline. So if the closest point is with the index 0 and it's 20% to the next point, it will return 0.2, for example. If the closest point is 1 and it's 50% to the second point, it will be 1.5. For example, for the arrows that we have here, this will be 0, this will be 0.2, 0.5, 0.7, 0.9, this will be 1.1, 1.3, 1.5, and so on. And taking this result, we use the same for function as before to get the closest smaller integer and set it here into the p1 local variable. Then we add one and set it to the p2. This will be our 0.1 and 0.2 that we'll use to calculate the values. For example, if we take this arrow here, the p1 will be this first point and the p2 will be this second point. Then we take the float part, not the integer, but the remainder of the number, and we set it into the weight. So with our example here will be 0.5. Our local variables 0.1 will be 0, 0.2 will be 1, and this weight will be 0.5. And then we use that points to take the value from our array, the value that we set for the 0.2, the value that we set for the 0.1. We subtract them and we get the difference of the coloring that we want to set. So, for example, if we want both of them to be red, the difference will be 0. If we want one to be green and the other to be red, the difference will be 1. And we can set values between that, so this will get just the difference between the 2 points. We'll multiply this difference to the weight. We add the value of the first point here because we already got only the difference, and now we need the absolute value, so we need to add back the 0.1 that we subtracted here, and we set that as a final weight and return it from our function. So let's recreate that here into our tool. Let's create a new function. Let's call it get covering weight, and for this function we'll need one input which will be the location, and this will be a vector, and we'll have a one output that will be our final weight, and this will be a type float. Now let's do our calculations. As you saw on the example blueprint, we'll find input key closest to world location, and we'll put this location that we have as an input here. We'll for this and set our result to one local variable called p1, which will be of type integer. We'll have p2 of type integer as well. We'll have weight variable with the type of float. We'll have difference weight variable with the type of float, and final weight variable with the type of float. Let's first set the 0.1 variable. Now for the 0.2 we just add 1 to the 0.1, and we set it immediately after. For the weight, we need to set it from the remainder of this value divided by 1. So type mod, this operation is called modulus, divide by 1 and set the remainder to the weight. And now, using these variables, we calculate first the difference in the weights by taking the weight at 0.2, subtracting the weight at 0.1, this will be our difference. And then, in order to calculate our final weight, we take our weight, we multiply by the difference, and then we add the value from 0.1, and we return this final weight value from our function. Let's go back to the construction script. Use our function. Let's make this function a pure function, so it doesn't have this execution inputs. So we input the location and we get the final weight here added to the custom data value that's driving our material core. This should be set to world. As I said, our function is using the world location. Don't forget that. And I think that everything should be fine now. Let's test. Select our spline tool and set our values. It's covering all the arrows the same, so we must have some error in our function. Let's check everything again. We're taking the world location. Actually, this is the So we are taking the world location, we're using floor value to return this input key. We're using the floor value to return 0.1, 0.2. We're setting the weight. We are not adding here the calculated weight. Now it should be fine. Okay. You can see that now, if we set the value for 1 point, it will calculate for each arrow how much of this first point and how much of the second point it should be using for the coloring. This is everything for the coloring, for the placement and the orientation of the arrows. The only thing left is the disappearing in the distance. You can see in the original material we have in the opacity this function. I'll just copy it into our new material and explain the notes. I'll paste it here. I'll change the material type from opaque to translucent. This will give us the ability to set up the opacity. We'll connect this to the opacity. And now let me explain the logic here. We're using the pixel depth, so this is telling us how far away is the pixel from our camera. We are subtracting 1000 from our pixel depth, then dividing this number by 500 in order to bring it closer to the 0-1 range that we need for our opacity. Then we clamp this between 0 and 1 to be sure that we are just getting the opacity values in the valid range, and we are using this as an alpha from our maximum opacity variable for our material to 0, that will be fully transparent in the distance that we set. So this is taking care of the disappearing of the arrows in the distance. You can see that they are fading away the further away they are from the camera, and we can see them when we're close. One other thing that you can do is, in order not to draw the arrows at all if they're fully transparent, you can go into our tool, and for the instant static mesh component you can set the co-distance to, let's say, 1500, and that way if the arrows are being fully transparent they will not be drawn at all. This will make it better for your GPU to render the scene. And that's everything you need for this tool. As you can see, you can draw very long lines with it. You can set up the colors for them. You can control the offset between the arrows, and you can offset them vertically. I hope that this tool will be useful for you. It's very popular in all racing games. It's very popular in the racing games, but you can use it to guide your player through the level for any type of game. If you have any questions, please comment below. You can subscribe and like the video, this will help a lot. And please, if you have any requests for other tutorials, write in the comments and I'll make sure to do my best to create the tutorial based on your requests. Bye for now, and I'll try to make the next tutorial sooner. Bye guys.